Some problem solving should perk me up a little bit. All right, so chemistry 3111. We left off kind of looking at these questions very, very quickly. And yeah, so it says here identify reagents that you're going to need to do these transformations. You will also need to use reactions from previous chapters. Well, when I solved these, I didn't write out any intermediates for these ones, but I'll put a few in here. Oh, my Bluetooth doesn't want to, my Apple Pencil isn't connecting. Just give me a second here. That's why. All right, let's try that instead. There we go. All right, so now my Bluetooth is connected. Let's give this the old college try. Well, the first one, you can see that it involves alpha halogenation. Right, if you want to put a bromine alpha to this carboxyl group, so meaning this carboxyl group, and this is the alpha carbon here, you're going to have to use the Hell-Volhard-Zelinsky reaction to do that. And if you don't remember the Hell-Volhard-Zelinsky, let's just go back a few steps. All right, back here, where was it? We looked at it towards the end. The Hell-Volhard-Zelinsky. Here it is, right here. Hell-Volhard-Zelinsky reaction. So it's taking a carboxylic acid, right, like this, and then you end up installing a bromine in the alpha position. So the first step is bromine and phosphorus tribromide. You make this alpha bromoacid bromide, and then you treat it with water, and it hydrolyzes the acid bromide to the carboxylic acid. But before we do that, we need to make the carboxylic acid, don't we? So that's going to require a little bit of Grignard chemistry, because we can take this benzyl bromide and we can convert that into a Grignard reagent. If we take it like this and we treat it with magnesium, then we're going to end up with this, where we have this nucleophile like that. Sorry, I had an extra carbon there, didn't I? There we go. So we're going to end up with phenyl, and then we're going to have this, and then we're going to have magnesium bromide like that. Okay. So the next thing is we're going to treat that with CO2. So I'll put here step 1, we'll do CO2. Step 2, we'll do hydronium like that. And that is going to give me this compound. So that's phenylacetic acid. And then to get to the final product, all I have to do is the Hell-Volhard-Zelinsky reaction. So in step 1, I'm going to treat it with bromine and phosphorus tribromide like that. And in step 2, we're going to hydrolyze it with water, and that's going to give us the product, which is this compound where we have the bromine installed here, and we have our carboxyl group like that. So overall, the first step is magnesium. The second step is CO2. Third step is hydronium to protonate to give you the carboxyl group. And then step 4 is going to be the bromine and phosphorus tribromide. And then the last step is going to be hydrolyzing the acid bromide with water, and you're done. All right, so 5-step synthesis, not too bad. The next one, again, it's going to be the Hell-Volhard-Zelinsky reaction, because you're making this alpha bromo carboxylic acid, but we need to take this primary alcohol and convert it to a carboxylic acid. Nothing is straightforward in this class, but I know you all know how to do that without any of my help. That's just the oxidation of a primary alcohol to a carboxylic acid, which we can do using chromic acid. So for that, all we need is sodium dichromate, sulfuric acid, and water, and that's going to give us the carboxylic acid. And then at the end, we're going to hit it with our bromine and phosphorus tribromide, followed by water. And so again, this part here is the Hell-Volhard-Zelinsky reaction, and this part right here, of course, is the Hell-Volhard-Zelinsky reaction. All right, what the Hell-Volhard-Zelinsky, right? The jokes write themselves. Anyhow, so we covered that one about the other one. They gave you the reagents for the Hell-Volhard-Zelinsky. So let's move on to 21.12, and in this one it says predict the major product when each of the following compounds, well, there's only one of them, so this is acetophenone, is treated with bromine together with sodium hydroxide, followed by aqueous acid. Well, we know that what happens in this reaction, it doesn't ask for a mechanism, but in the first step, what we do is we keep pulling off the protons that are on the methyl group and replacing them with bromines. so that we end up with this intermediate that looks like this. So you're basically converting the methyl group into a good leaving group, right? A methyl group is definitely not a good leaving group, but this CBr3 anion would be a good leaving group because it's stabilized by the 3 electron withdrawing groups. And so once you've made this intermediate, okay, and that's after the first step, then what's going to happen is that still in that first step, hydroxide ions are going to come in and act as nucleophiles. So we're going to get a tetrahedral intermediate, which is going to look like this. So I'll just replace the aromatic ring with pH for phenyl. So we have our tetrahedral intermediate, which looks like this. There's our hydroxide, and then we have CBr3. And again, that's going to be our leaving group. So we're going to lose our leaving group like this. And this is kind of the interesting part, because you might be tempted to think, well, this is the end. You know, the reaction is over because this is the final product. You would be right if you said this is the product, right? The product is going to be benzoic acid, but this is not the end of the reaction. And the reason why is because what happens next is the CBr3 anion, which is the conjugate base of bromoform, is going to come in and abstract this proton. So you actually end up with, after the first step, you actually end up with the carboxylate, okay? So you end up with the carboxylate anion like this, and that is why you put hydronium in. So in the last step, you put hydronium, and again, I know you don't need my help with this mechanism, but we'll just write it down. So what's going to happen is you're going to do a proton transfer like that, and you're going to end up with your benzoic acid. Okay, so what's the point is that in the haloform reaction, what we're able to do, and this is the most important part, okay, I'll write it down here. In the haloform reaction, you can take a methyl ketone, so there's just a plain old methyl ketone. I'll even write CH3 in here. And after 2 steps, the first one is sodium hydroxide and bromine. The second one is just aqueous acid. But after those 2 little steps, you end up with a carboxylic acid. Now, if you're wondering why you keep yammering on about this, well, what did we learn in chapter 20? A whole lot of carboxylic acid chemistry. So you can kind of think about it that way. Think of all the different reactions that we learned in chapter 20. So you can take a methyl ketone, which is, you know, maybe relatively inexpensive, and then you can, you know, do all kinds of things with that methyl ketone, convert it into a carboxylic acid, and Bob's your uncle. Anyhow, so once the CBr3 anion pulls off the proton, you end up with, this would be CHBr3. This is actually called bromoform. You heard me say the word a few minutes ago. And you guys know that CHCl3 is chloroform, which was used as an anesthetic back in the olden days, okay? And if you use iodine, you get CHI3. This is called iodoform, okay? And I'm not going to go into the details of the iodoform test. However, CHI3 iodoform is actually a yellow precipitate. So it's actually a yellow precipitate. And so one of the old-timey, you know, chemical tests before NMR to determine whether you had a methyl ketone or not was to do this reaction. And if you got a yellow precipitate, you could conclude, oh, I must have a methyl ketone. And so it's something that we don't usually get our students to do in the lab, but in lower level labs, we get students to do the haloform reaction from time to time. Anyhow, all right, so let's take a look at these ones here. This is 21.13. So we're starting out with this alcohol, and we want to make this ester. Well, you can see that you could make that ester, right, from the corresponding carboxylic acid. That would just be a Fischer esterification. And how would we go from here to a carboxylic acid? Well, the first item of business is going to be to convert this alcohol into a ketone. So if I just use PCC, then I would have the methyl ketone, and as I just, you know, yammered on about for the last how long, we could do the haloform reaction. So in the first step, we're going to use sodium hydroxide and bromine, followed by aqueous acid, and that's going to give us the carboxylic acid that we're looking for. All right, and then the last step is just going to be a Fischer esterification reaction. So I'm going to remove my retrosynthesis and just kind of park that over here. So we'll say to go from here to here, you're going to use ethanol as your alcohol, a catalytic amount of acid, and you're going to remove water. So again, this one involves the haliform reaction, right? This is the haliform reaction, and then this would be Fischer esterification. All right, the next one, we have an imine or a Schiff base, and we want to make an amide. And of course, we can hydrolyze. This is what I told you last class. We can hydrolyze the imine with H3O plus to the ketone. And of course, it's a methyl ketone. And so based off of that, we can convert it into a carboxylic acid using the haliform reaction. So using sodium hydroxide and bromine followed by H3O plus, that gives us the carboxylic acid. Now, to make the primary amide, what we're going to do first is we're going to make the acid chloride, and of course we make that using thionyl chloride, SOCl2. So that's going to give us this compound like that. And then to get to the primary amide, you're just going to use excess ammonia like that. There we go. So borrowing some chemistry from chapter 20 for sure. So this one is kind of a mixture of chapter 20 and 21, you know, kind of all rolled into one question. All right, there we go. So now we're going to get into something new, and we're going to talk about aldol additions, and we're also going to talk about aldol condensations in a little bit. And then after that, we're going to get into what are called crossed aldol reactions. So section 21.3 is kind of a lengthy section because we also look at intramolecular aldol reactions, and then we'll solve a few problems. So after that, we'll get into what's called a Claisen reaction. But anyhow, let's start off here with the aldol addition. And I've taught this long enough to know that what you got to know is that when we look at aldol addition, so when we're doing aldol addition, there's going to be no heat in the reaction. Okay, so we don't heat the reaction up at all. But when we do an aldol, what's called an aldol condensation, we heat. Okay, and the difference between the two is the heating isn't all that vigorous when we do an aldol condensation, but that's the difference between the two. Okay, and you do have to understand the difference between aldol addition and aldol condensation. So let's take a look here. It says, recall from last lecture that when aldehyde is treated with an alkoxide like sodium hydroxide, methoxide, ethoxide, in equilibrium forms where significant amounts of both the enolate and the aldehyde are present. So what that means is if you had this aldehyde here, this is one of the second simplest possible aldehyde. The first one would be formaldehyde, but that has no enolizable protons. But this is acetaldehyde, okay, or you could call it ethanal, either one is fine. If you put that in sodium hydroxide, based on what we talked about last class, you would actually have a mixture of both the aldehyde and the enolate, right? You'd have both of these present in the same flask. So in your reaction flask, what you have stirring around is both of those. You have the aldehyde and you have the enolate together, okay? So what does that mean? That means that you can have a nucleophilic attack by the enolate on its corresponding aldehyde. So you can see that that's where this product comes from, and we call this an aldol addition product. Sometimes we call it a beta hydroxyaldehyde or ketone because you can see that we have a hydroxyl group where on the beta carbon of our aldehyde in this case. So we call it an aldol. You can guess why, because it has the properties of both an aldehyde and an alcohol. And again, notice the location of the hydroxyl group. Where is it? It's on the beta carbon, okay? So it's on the beta carbon. So I bet you could have figured out this mechanism without me even showing you this slide. If I had given you all an assignment and said, oh, see if you can come up with a mechanism. This is exactly what you would have come up with. You would have pulled off the proton off of the aldehyde. Remember, only some of them. So in our reaction flask, we have both of these present, right? We have the enolate and we have the uncharged form. And so the enolate is going to be able to do a nucleophilic attack on the uncharged form. And then we end up with this alkoxide here. And then we have a proton transfer, and we're done. And remember, the hydroxyl group is on the beta carbon, and we call this an aldol, okay? And this is the product of an aldol addition, Okay, an aldol addition reaction. So let's review. What are the conditions for the aldol addition reaction? The conditions for an aldol addition reaction are sodium hydroxide and water. Okay, and I'm going to add something to this. I'm going to add no heat. Okay, there's no heat when we do an aldol addition reaction. We don't have to heat it up at all. So it turns out that if you take a simple aldehyde, right, like this one here, this is, you could call this butanal, or you could call it butyraldehyde. Either one is fine. Okay. If you put that in sodium hydroxide, you have a mixture of what? You have the enolate, okay, and then you have the uncharged form like this, and so the enolate can attack like this, and this is just me kind of rehashing the mechanism that we just looked at, right? And then after a proton transfer, you end up with the aldol addition product. So notice this is your alpha carbon, this is your beta carbon. Well, it turns out, like I was trying to say, when you have a simple aldehyde, that the aldol product actually is favored. But if you have a ketone, it usually doesn't favor a ketone. Okay, it turns out they actually just mostly have the ketone intact, and you only have a little bit. You see here, it's only 20% of the aldol addition product. So if you have the reverse process occurring, okay, so if the process goes forward, but then it goes back to your initial starting materials, we call that a retroaldol reaction. Well, the good news is this. If you know the curved arrows for the formation of the aldol, okay, so aldol addition, the retroaldol reaction is just the exact reverse, okay? So all we do is a proton transfer to make the alkoxide, and then look very carefully. You have an enolate leaving, enolate behaving as a leaving group here, okay? So the enolate takes off in this case. And the reason why we can do that, because you might think, well, hold on, that's a carbanion. You can't lose that. And I've only had a few students ever bring that up, but it's very sharp to pick up on that. But I said, actually, it can. This can function as a leaving group. Why? Because it's resonance stabilized. Okay, so since it's resonance stabilized, it can function as a leaving group. Then after a proton transfer, there you go. You're right back from whence you came. Okay, so that's the retroaldol reaction. Now, it says here, if you do the same condition, so a catalytic amount of acid or base, and you heat it up this time. So you see it down here. It's just sodium hydroxide, water, and heat. So what's the difference? Is heat. Okay. It says here, when the aldol product is heated under acidic or basic conditions, you get an alpha beta unsaturated carbonyl. So you see that we have a double bond between the alpha and the beta carbons. And of course, we lose water in the process. So an aldol condensation occurs when the reaction is performed at elevated temperatures. Now, I wrote something down here. What I wrote for myself, okay, when it says elevated temperatures, and I mean, I wrote it for myself, but I'll give you the information. As I wrote down here, conditions are only slightly more vigorous. Okay, so there's kind of a delicate balance here between getting the aldol addition and the aldol condensation product. But you see here, again, the only difference is adding heat. Okay, so heat is the key here. So again, no heat, aldol addition. Heat it up, get the aldol condensation. If you want a summary of it, here it is. Okay, if you were to take these two aldehydes, we saw the aldol addition product. So how do we get that? Let's pencil it down. We'll practice. We use sodium hydroxide and water. Now, I like to write sometimes no heat. Obviously, you don't have to write something that isn't there. Okay, that's not required whatsoever. But if you do the aldol condensation, it's the same thing. So we'll put here sodium hydroxide, water, and we'll put here heat. Okay. So we're going to heat that up. Now, if you're wondering, what's the driving force of this reaction? Well, it turns out that the driving force of forming the alpha beta unsaturated aldehyde, I'll put here driving force is formation of a conjugated system. Right? What's conjugated? Conjugated is when we go double, single, double, right? And we have that here. So in the alpha beta unsaturated aldehyde, or the product of aldol condensation, we get something that is stabilized because why? It's conjugated. Well, let's move on from there. Now, the mechanism of aldol condensation. The good news is we covered this part already. Okay, this is not new. This is like, you could say, see previous slides. Okay, we already looked at this mechanism, and I told you I expect you to know that part. But then to do the elimination of water, all we do is we do a proton transfer followed by a loss of a leaving group. And this one here, we call this the E1, this reaction here, we call it the E1CB reaction. I'll use my blue pen, the E1CB. And the CB stands for conjugate base. Okay, so you remove a proton, and then you do an elimination here with the conjugate base of the starting material. I'm not going to quiz you on E1CB or anything like that, so don't stress about it. But that's what it's called. It's called an E1CB elimination. Anyhow, but there you go. So that's how you form the alpha beta unsaturated ketone. And remember, this is a conjugated system. Okay, so that's the driving force of the reaction. Now, I know you're all very astute, and you probably noticed something about this product, which is that it happens that they drew the trans product. Now, if you're wondering, can you have the cis product? Absolutely. Okay, you can end up with both of these stereoisomers. However, when you do an aldol condensation reaction, the major product is usually just going to be the one that's less sterically hindered. Okay, so we'll put here fewer steric interactions, major product. Honestly, you guys, while I'm lecturing, I'm trying to think of an exception, and I can't even think of one off the top of my head. Maybe there is, but it's nothing I could come up with that quickly. Well, let me show you an example where you can't even isolate an aldol, okay? And I've been a victim of this a few times in my life, where I said, oh, I'll just make this aldol product here, okay? There's nothing wrong with this. This is a beta hydroxy ketone, so this is the product of an aldol addition. So we could even write here aldol addition product. Okay, you can see this is alpha, this is beta, so it's a beta hydroxy ketone. Well, it turns out that when you take acetophenone and you treat it with sodium hydroxide, even if you don't heat it up, okay, even if you have it, well, even right here, no heat, it's still going to go all the way, okay? It's going to do that E1CB, and you're going to end up with the alpha beta unsaturated carbonyl. What do you think the driving force is here? I mean, hopefully it's relatively obvious, okay? Is that you form a highly, right here, you form a highly conjugated system. And there's nothing you can do to stop it, really. So I don't even know if you could isolate this aldol. It's too high in energy, because once you lose that water molecule, I mean, you end up with something that's completely conjugated the whole way through. I mean, I don't even know how to draw that, but it's just completely conjugated. So there you go. So give me a thumbs up if you're with me on at least the condition differences between aldol addition and aldol condensation. One uses no heat and the other one uses heat. So the condensation uses heat. All right, cool. So the yields for the condensation are usually greater than for the addition reaction. You see here that if you take cyclohexanone and you put it in sodium hydroxide, and this would be like, you know, put some ice in there or something, you only end up with the beta hydroxy ketone. So this is the aldol addition. So aldol addition product in a pretty low yield, whereas this is the aldol condensation product, and you end up with that in a really good yield when you warm it up. Okay, so aldol condensation, a lot more useful. I'll be honest with you, I haven't done that many aldol condensation reactions in my life. I've done a few, but it certainly wasn't part of my graduate work or anything like that. Now, as far as the skill builders go, you know, I don't bring up the skill builders a ton in class, but there is a skill builder. Let me find it here. I had it open, and then I think I closed it. It's skill, just bear with me. Skill builder 21.3. So skill builder, so already here, skill builder 21.3, okay, is a really helpful skill builder because it shows you how to draw the products of aldol condensation. And I'm going to try to do that with you as well in a little bit. But before we do that, I want to, just kind of propose something here to you. What if, you're like, oh boy, where's he going with this? What if you had two different aldehydes or ketones and you tried to do an aldol reaction? So let me show you what I mean. Let's say you took acetaldehyde and propionaldehyde and you put them in sodium hydroxide and you're like, well, what am I going to get? Well, hold on. You've got both of these compounds neutral, but you also have their enolates. So that means you'd have this enolate and you'd also have this enolate. So that means that this compound can react with the same compound. This compound can react with this one. This compound, this enolate can react with itself, and this enolate here, right? So we end up with 4 different scenarios and 4 different products. I don't know about you guys, but when I see a reaction where I get 4 different products, okay, and you're like, Mr. Dion, that was chapter 7. Like all you did was talk about SN1 and a bunch of E2 products, right? Or SN2 and a bunch of E2 products. I get that. But the point is here is that 2 different aldehydes can give you 4 possible aldol products, okay? And this is not good, right? This is not very useful. It would be very difficult to purify these, to distinguish these from each other. And so what we do to avoid, this, I'll just put here, avoid this question mark. Is there a way to do that? And the answer is yes. We use what are called crossed aldol reactions. So take a look here. Now it says here, a crossed aldol reaction is only practical if the number of products can be minimized, which is achieved in one of 2 ways. So what are the ways that you can minimize all those different products, right? This is a kind of a crazy reaction. I'm just looking at it and thinking about it, like, how would you even purify that? I'm not really sure. I suppose there's a way, maybe HPLC or something. But anyhow, so a crossed aldol reaction. So how could we react these 2 compounds and limit the amount of products? Well, it turns out that, first of all, formaldehyde has no enolizable protons, right? It has no alpha protons, so it can't form an enolate. It's impossible. The only compound here that could form an enolate would be this. So that means that if you put these 2 compounds together in a flask with sodium hydroxide, you're going to have those 2 compounds and you're going to have the enolate, okay? So you might be saying, well, you can get 2 products because you can get a nucleophilic attack here or you can get a nucleophilic attack here. Well, it turns out that if formaldehyde is your electrophile, it's probably only going to do the nucleophilic attack here. Why? Because formaldehyde is just so stinking unhindered that it actually takes considerably more energy to do the nucleophilic attack here, so it doesn't happen, okay? So that is one way to limit it, okay? Again, there's probably some limitations to this as well, but you do limit the number of products. So that's one way, is to kind of use formaldehyde, which has no enolizable protons, but it's such a good electrophile because there's nothing hindering the carbonyl carbon. Okay, what else can you do? Let's see here. It says relatively unhindered without alpha protons. Now this one here is a little bit interesting because if you were to mix these 2 in a reaction flask, you're only going to have the enolate of this compound. Why? Because there's no alpha protons here, right? There's no alpha proton on this carbon, and this is a hydrogen, not a carbon. So the only enolate that we could form here would be this compound. And so what's going to happen is it's going to react with the benzaldehyde. And the driving force here is that you're going to end up with something that's completely conjugated. So that's going to push the reaction forward here. So I'll even write that in here. We'll just write here, highly conjugated. So that would be a driving force here, okay? And if you're wondering, do I need to know these specific examples that you're going over? Yes, you do, okay? So make sure you make a note of these, okay? So the next one, benzaldehyde, you end up with such a highly conjugated system. And so another one is this one here, and this is something I have done a bunch of times in my life, okay, is what's called a directed aldol addition. Now this one is kind of an interesting reaction, and I don't want to take up too much valuable class time by just, talking about how you would do this. But the way you do this is you actually have a reaction flask that has LDA in it, okay? If you guys remember LDA from the last class, it's lithium diisopropyl amide. So your base is this. It's diisopropyl amide. It's a very strong base. If you have lithium like that. That's LDA. Okay, so very strong base. And then what you're going to do is you're going to take your ketone that's shown here in red, which is acetone, okay, and you're going to put that into the reaction flask like this. So as soon as the ketone hits the LDA is going to rip off a proton, so that in your reaction flask, after the addition is done, all you're going to have is this. It's just the enolate of the aldehyde. Okay, so then what's going to happen is then you're going to take this compound, okay, I'll use a blue circle, which this is propionaldehyde. You're going to put that in a pipette, and you're going to pipette this into here. So as soon as this gets pipetted into the flask, this is going to do a nucleophilic attack on that, and then you get this intermediate here. You add water, and you end up with your aldol addition product. Now, if you're very astute, which I know you all are, you might be saying, well, if I dump this compound, this blue aldehyde, into this reaction flask, how am I guaranteed that a nucleophilic attack is going to occur and that it's actually not going to do a proton transfer where it's going to rip off this proton and form the other enolate? That's a good question. And what I would say to that is that the success of this reaction is actually limited by the rate at which the enolate can deprotonate the electrophile versus its nucleophilic attack. But we're going to assume that nucleophilic attack is going to occur. There you go. So that's how you would set that up. Again, I'm not going to ask you a whole essay about adding this to this and all that kind of stuff. It's just kind of me fleshing out the idea. And if you have to go back and watch the video again, it might help you understand, what the heck is going on. Well, before we can wrap up section 21.3, there's one more part we have to cover, and that is an intramolecular aldol reaction, right? So far, we've only looked at intermolecular aldol reactions between two aldehydes or ketones, or an aldehyde or a ketone. Well, what if you have two ketones in the same compound, right? There's a ketone here, there's a ketone here. If I heat that with sodium hydroxide, I'm going to get an aldol condensation product. But let's think about this. If I just examine this carbonyl here, okay, I have the alpha proton in blue, and then I have the alpha proton in red. Which one of those protons am I going to pull off preferentially, because they'll both make a resonance stabilized enolate? Well, the answer is it's actually going to pull off the proton in red to make this enolate. Why? Because when the nucleophilic attack occurs like this, you would end up with a 1, 2, 3, 4, 5-membered ring, and you see that right here. If you had deprotonated where the blue proton is, so let's just imagine you did that. If you pull that off here, then your nucleophilic attack is going to be like this. Then you'd have a 1, 2, 3-membered ring. Is it doable? I suppose. But what's preferred in organic chemistry? Is it going to be a 5-membered ring or a 3-membered ring? Well, if you go back to our chapter on alkanes and cycloalkanes, you know that it's a 5-membered ring. And so that is what's going to happen, is we are going to form the enolate here, okay, on the terminal carbon. It's going to do a nucleophilic attack like this. We do a proton transfer, then we do our E1CB, and we end up with our alpha beta unsaturated carbonyl compound. So what you can use as a rule of thumb is that only 5 and 6-membered rings are going to form well this way. We're not going to form any 4-membered rings or 3-membered rings doing an intramolecular aldol condensation reaction. So with that in mind, question 21.14 says predict the major product obtained when each of the following aldehydes is treated with aqueous sodium hydroxide. And notice that they say here no heat. So what that tells you is that these are going to be aldol addition reactions. So here's what we're going to do. We're going to do this. Imagine that you have this compound, okay, the initial starting material, and you also have the enolate. Okay, so you have both of these in the same reaction flask when you heat this up, when you put this in sodium hydroxide. So then what's going to happen is that this is going to do a nucleophilic attack on here, and then we're going to do a proton transfer. So we have the nucleophilic attack, which we just drew. Then there's going to be a proton transfer. So what are we going to end up with? Well, I'm going to take the part in blue, and I'm just going to kind of twist it here to make it easier to draw. But it's going to look like this. And I'll put pH to represent my aromatic ring. So now, if I count these carbons, 1, 2, 3, like that. So let's draw very carefully. So here's the bond that I made. This is carbon 1, 2, 3. And then we have another aromatic ring. So 1, 2, 3. And on carbon number 1, I'm going to have the oxygen from my former aldehyde, and it's going to have a proton. Why? Because this is aldol addition. So there we go. That's that one. The next one, we're going to imagine we have the starting material, and we're also going to have the enolate. What's my enolate going to look like in this case? It's going to look exactly like this. So now this enolate can act as a nucleophile, and it can attack here like that. So what's it going to look like? This one's going to be a little trickier to draw. After the nucleophilic attack and the proton transfer, we're going to end up with something that looks like this. Just bear with me as I do my best to draw this. So we end up with our carbonyl here, like that. Then we're going to have, maybe I should have put this in blue. Oops. Because this was, this comes from the enolate. So then that's, no. Then that's going to be attached to, come on, pen. That's going to be attached to the alpha carbon, which has a hydroxyl attached to it. And then it's going to have the 6-membered ring. All right. So let's see here. Nope, I put it in the wrong spot, didn't I? I was like, that's not right. So alpha carbon, beta carbon, there we go. So we'll just do something that looks like this, and then something that looks like that. Not my prettiest work, but you get the idea. So again, no, I drew it wrong again. I knew there was something funky about this. Let me try again. So this is my alpha carbon. This is my beta carbon. Good. So this is where my hydroxyl is going to be, and this is where my cyclohexyl group is going to be. There we go. Third time's a charm. All right. Give me a thumbs up if you're with me on the aldol addition. Is everybody following me on this mechanism? Cha, anybody else? Aldol addition? All right. Okay, well, the next one is the one that involves the skill builder. So skill builder, so we'll put here skill builder 21.3. That's the one that helps you draw the product of the aldol condensation reaction. And so what it's asking us to do here is it says, give us the products if we were to heat the following compounds in the presence of aqueous sodium hydroxide. Now, you could do it the exact same way I did it here, and then just do the E1CB. That will work, but I'll show you my kind of shortcut if you want to know. So here's what you do. You start by drawing the starting material, which is going to look like this. Okay, so I'm just reproducing it the way they did it. So I'm going to copy and paste that. Okay, and here's all you do. Oops. What you do is this. You're going to take the oxygen from one of these compounds, and you're going to redraw it in a new color. No, that's not a new color. There we go. And then you're going to draw the 2 alpha protons on the other compound in another color. That is where the water is going to come from. So then what you're going to do is you're going to take this compound and you're going to put it like this, okay? And after you lose water, this is where the double bond is going to be formed. It's going to be between these two. So you see how I have them kind of touching like this? If you were to delete the blue molecule, or sorry, the blue atoms and the blue bonds, that would be the actual product. Now it's kind of sterically hindered the way that I have it drawn. So what I'm going to do is I'm going to move all of this down here. Okay, and I'm going to redraw it. So after the proton transfer, nucleophilic attack, and another proton transfer, I'm just going to move one of those cyclobutyl groups over here like this. So then I can draw the aldehyde like this, and then I'll put my double bond here, and I'll just put the, there we go, the cyclobutyl group out like this. Now again, if you drew this, so look, if you're paying close attention, and if you had drawn, this with the carboxyl, let's say you put your 5-membered ring down here, and you drew a double bond like this, and then, yeah, no, that's still not right. Yeah, that is right. If you had drawn this, it's the same thing. It's totally fine. All I drew, the difference here is that this is the Z compound, and this one I drew the E compound. But I wouldn't pick on you about that right now. I would just say that the least sterically hindered one is probably going to be favored. That's all. But both of them would be fine to draw. All right, the next one is in the same vein. If we take that and we put it in sodium hydroxide and we heat it up, what are we going to end up with? 1, 2, 3, 4, 5. There we go. And then we're going to have our double bond here. Then we're going to have 3 carbons on each side. So 1, 2, 3, and 1, 2, 3. There you go. Nothing to it. Now, if you're wondering, how did you do that so quickly? The way I did it was like this. Okay, I drew another molecule of the ketone in this case. I'm going to replace the oxygen with a blue atom, and I'll put 2 of these blue atoms here like this, and that's where my water is going to come from. To see what my product looks like, all I have to do is touch the double bond there, and that's the product. So that's what I drew. Okay, so I just connected those 2 molecules after I removed water, just like that. All right, so of course in both of these cases you could write, you could write plus H2O and plus H2O. All right. Now with this, these compounds, these compounds, it's asking us to come up with the reactants. And it just says identify the reagents that could be used to produce each of the following reactions. So you can see the first one is an aldol addition because we have a beta hydroxy ketone. And this one is an aldol condensation. And we can see that because we have an alpha beta unsaturated ketone. And so this is the way I solve these, is if this is your carbonyl, and this is your alpha carbon, this is your beta carbon. So this is where the bond was formed, right? Same thing with the one on the bottom. Here's your carbonyl. So this is your alpha, this is your beta. So where that double bond is, that's where the bond was formed. So then when you do your retrosynthesis, all you have to do is this, okay? Oops. All you got to do is this. So we'll draw the ketone out the way it is. We don't touch that at all. And then everything else, all of this part over here, that's where the starting aldehyde is going to come from. So the aldehyde in that case would look something like this. So there we go. So it's going to be 1-methylcyclohexane carbaldehyde. And of course, all you would do is put that in sodium hydroxide and water, and it's going to give you the product. So we could just say, take these 2, come on, take these 2, add them together, and then we just do it in sodium hydroxide, water, and then you end up with the product. Keep in mind, no heat, okay? No heat required. And then for the next one, it's in the exact same vein. So when we do our retrosynthesis, we're going to have the starting ketone, which is going to be cyclopentanone, and our starting aldehyde is going to be this aldehyde, which you probably recognize like that. Oops. That's benzaldehyde. So there you go. So that's how you come up with your conditions. And again, this one, your conditions would be sodium hydroxide and water. And of course, you would add heat. And that because it's an aldol condensation. And that's going to give you your product. Just like that. All righty. So let's try this one here, and then we'll take a short break. This one says draw the mechanism for the following transformation. So we're starting out with this diketone, and we're making the 5-membered ring. So obviously we're forming the enolate here. So we can start by drawing that part of the mechanism. If we put in this proton here, and then I have my hydroxide like this, the hydroxide is going to pull off the proton, and I end up with the enolate. So let's draw the enolate, which is going to look something like this. All right, so now I have a good nucleophile and I have a good electrophile in the same compound. So my nucleophile is going to attack my electrophile like this. So now if I count my carbons very carefully, okay, I'm going to have a 1, 2, 3, 4, 5-membered ring. So I count here 1, 2, 3, 4, 5, like that. I have my carbonyl here. So if this is carbon 1, it's attached to carbon 5. So this carbon is going to have the alkoxide, and a methyl group on it. And so then we do a proton transfer with water. So we do a proton transfer like this. That gives us the beta hydroxy ketone, like that. And then we do the E1CB reaction. So we do the E1CB. So let's see here. Let me try it out here. So the hydroxide ion is going to pull off our proton. That's going to pull off our proton like this. It gives us the conjugate base, which looks like this. Then we have our methyl group and our hydroxyl group. And then we form the double bond. Just like that. So there we go. And that takes us to the final product like that. And again, this is our E1CB reaction mechanism right there. So that covers intramolecular aldol reactions.